Hello guys, Teaches again. Today we're going to be discussing Lewis structures and Vesper theory. So the first thing I want to introduce is the electron dot diagram, and it's just a means of representing the valence electrons around an atom. So for example, hydrogen, since it only has one valence electron, we draw one dot. For oxygen, we draw 6 dots. Chlorine, 7 dots. And Lewis structures are we can expand on this idea to uh, we can expand on this idea to make Lewis structures, which are essentially models that drawn on paper that represent molecules of covalently bonded structures. So most commonly molecules and polyatomic ions. I suppose an interesting note to note here is that a molecule, although what we define in a molecule in topic one was sufficient for topic one stuff, I think we should bring up what I would refer to as a simplified version of the IUPAC official definition, which is essentially the smallest repeating unit that has some type of structure to it. More or less is what it's saying. There's some formalism there, which involves quantum mechanics, which I won't get into because that's well beyond the scope of any high school syllabus. Um, Regardless of that, molecules are groups of atoms that are, well, they're not that, but it doesn't really matter. Polyatomic ions are similar, but they have a net charge as opposed to just a typical molecule. The Lewis structure model is a localized electron model, which basically means that the electrons are assumed to be in one. They're assumed to be localized to one specific region, which, while this is great for a lot of molecules, actually, there is. We'll go on to discuss resonance structures later in the same lecture, and for that you can draw multiple Lewis structures that are valid, and it actually turns out that those electrons are sort of orbiting around the whole molecule, I guess. Yeah, to put it simply. Anyways, so what do we need to what do we need to know for a Lewis structure? A covalent bond consists of a line, whereas a lone pair consists of a pair of dots. Some rules for drawing out Lewis structures. You don't have to go through this process every time, and once you discover, once you do enough of them, you'll generally tend to get the hang of a few patterns, which I'll discuss after I go over the formalism. But let's go over the formalism first. So, firstly, add up all the valence electrons from all the atoms based on the formula, the molecular formula. Consider total charge as well. So negative charges indicates additional electrons, whereas positive charges indicate a deficiency of electrons. So for instance, a molecule of CO2 has, so there's one carbon and two oxygen. One carbon has 4 valence electrons. Oxygen has 6 valence electrons. Since there's 2, you get 4 plus 2 times 6, which is 16 total. Then you decide on the central atom, which generally tends to be the least electronegative atom, the atom written first in a formula, the atom of which there's only one, or they tend to be carbon, nitrogen, phosphorus, or sulfur, and not hydrogen. In CO2, C is less electronegative, written first, and singular, so therefore carbon is central in CO2. We can use a pair of electrons to form a bond between each pair of atoms that are bonded together, so draw a line for each bond. So draw one bond first, linking each one, and then subtract it from your total valence electron count, and then subtract for every bond, subtract 2 electrons from the total number of valence electrons you started with originally. This will make sense if I do a worked example. And then lastly, put the remaining electrons in pairs on the other atoms, except hydrogen, if there's room for it. Put them on the central atom as a last resort, generally. So 16 minus 4, so we draw 4 here, means 12 valence electrons still not drawn, so we can do dot 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 dot, and now there's 6 valence electrons. But there's something wrong here. Lastly, we make sure everything obeys the octet rule. So as you can see here, carbon does not obey the octet rule since there's only, well, we count a bond as 2 electrons, so 4 there. So we need to draw in 2 more bonds. So share more electrons, so we put this bond here and this bond here, and there we go. We have a full octet for everything. Remember that these count as 2 electrons for the oxygen, so we have 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. There we go. Everything has 8 bonds, which is what we refer to as the octet rule. There are exceptions to this, quite a few of them. It's even been proposed that this just be called the octet suggestion, since there's so many exceptions, one of which we're going to cover like in 2 minutes. So yeah, let's do that. Multiple bonds, one of which is actually hydrogen, which will only have 2 electrons in it as a Lewis structure. This is called the duet rule. Since hydrogen's noble gas electron configuration makes it has the same configuration as helium, it's not really a violation of the spirit of the law. It's more just the word of the law. It obeys the law in spirit, more or less. Next, we talk about multiple bonds. So it's possible to have a single, a double, or a triple bond between a pair of atoms. Generally, you'll only add these during the last bits just to make sure that the octet rule is obeyed. And with these multiple bonds, the number of electrons shared between the two atoms is 4 or 6, depending, instead of the usual 2 electrons with a single bond. Note that a double bond is not a bond, but it's 2 bonds. And when we go into the higher level stuff, there's a bit more detail with that. But for now, we're going to put that aside and leave it for the higher levels at a later time. The more bonds there is, the shorter the distance between the two atoms is closer, so the shorter the bond is, so the more bonds between them. So a single bond is the longest, a triple bond is the shortest, and the rationale behind that is more or less, since there's more bonds, there's more electrostatic forces of attraction acting on the two nuclei, so therefore they tend to come closer together as a result of more electrostatic force pulling them together. So let's draw some Lewis structures. So for example, let's draw this one. Ammonia, NH3. So if I move over to my other screen, so let's first do a count of valence electrons. So hydrogen has 1 valence electron, so there's 3 times 1 plus 5, which is 8. Now let's draw a thing. So nitrogen is the although hydrogen is technically the least electronegative atom, as we stated before, nitrogen, carbon, and all those other elements there tend to be central atoms. So nitrogen is the central atom. Let's draw a bond each to H to H to H, and we have 1, 2, 3 bonds here. So subtract 6, and we have 2. And since we can't put them on the H's, since they already have a full duet, we can put them on the nitrogen here, so we'll put a lone pair there. Ta-da! There we go, the Lewis structure for NH3. Let's do another one. I need to get a better fucking eraser or something. I don't know. Please, yeah, guys, please subscribe so that I can use the YouTube ad revenue, the 2 cents of ad revenues to, I don't know, get a better fucking thing than Word, fucking MS Paint. But regardless, let's do another one here. CS2, carbon disulphide. So carbon has 4 valence electrons and sulfur has 6, so plus 2 times 6, which is 16. So we draw the carbon here first, since it's the least electronegative element. Draw a sulfur, and then lone pairs. So 12. Draw a lone pair. And ta-da. And then make sure everything obeys the octet rule. Clearly carbon is not, so we'll put a bond there, we'll put a bond there. And ta-da, we have carbon disulphide. I don't think it's worth going over any other examples, but I will do the whole shortcuts thing now. Generally, you don't have to go through this whole process always. If it's a polyatomic ion, I would actually just go through the entire process because it just makes your life easier. No, it's honestly just easier, but for most molecules, you'll generally what you'll realize is that carbon tends to form 4 bonds, nitrogen 3 bonds, oxygen 2 bonds, halogens and hydrogen 1 bond. And then expanding that idea even further, group 14 tends to form 4 bonds, group 15 tends to form 3, 16 2, 17 and 17 1, hydrogen 1, and that will make your life a million times easier because you can sort of do it mindlessly. Although it's not on the standard level syllabus, I'm going to go over formal charges anyway. Lewis structures involve a model of localized electrons, i.e., they tend to be in one region. However, not every molecule has this when we discuss resonance later on. And to determine where a charge is, and for this case of polyatomic ions, the charge must also be localized. Therefore, we use the formal charge to do that. Formal charges, there's a formula for it. I'm not going to use it. I'm going to teach you a different way. Basically, what you can do is when you count for the octet rule, you generally count 8 and 2, so this is octet duet. However, if you count each bond as one electron, right? You count each bond as one electron, and then you compare the number of electrons each atom has compared to if it was neutral. So in the case of hydrogen, we count this bond here as one electron. It normally has one valence electron, so there's no formal charge. Whereas with oxygen here, we have 1, 2, 3, 4, 5, 6. Remember, we count the bond as one electron, 7 valence electrons. No, oxygen normally has 6 valence electrons. 7 minus 6 is 1 electron more, so it has a formal charge of minus 1. So for NO3, I'm going to just do this. What I'm going to have to do is we're going to have to draw a Lewis structure for NO3. And I already know what this structure is, so don't worry about it too much. And it has a net charge of 1 minus. Oops, that's not obeying the octet rule. So there's a Lewis structure for that. We can note here, so 1, 2, 3, 4, 5, 6, so that has a formal charge of 0. We can have 1, 2, 3, 4, 5, 6. Remember that counts as 1, so that's 7. So that has a net charge of 1 minus. Same thing here, 1 minus, 1, 2, 3, 4, 5, 6, 7. And then with nitrogen, we have 1, 2, 3, 4. Nitrogen only has 5 valence electrons, so this has a charge of plus 1, a formal charge of plus 1. And these cancel, giving us our net charge of 1 minus. Alright, going back to the main screen here. Generally, when you draw Lewis structures, you want to minimize formal charges. So here, although this technically does obey the octet rule, there are formal charges here, plus and minus, which is still 0, but this just has 0 all around. So this is a more stable charge, more stable structure, since there's fewer formal charges. Exceptions to the octet rule, as we already discussed. Hydrogen is an exception to the letter of it, but not the spirit. However, there are still exceptions to the octet rule, which are group 2 and 3, which tend to be stable with only 2 or 3 bonds. They tend to be stable with 4 or 6 electrons respectively. As you can see here, here's why. This is a more stable structure because it has no formal charges. It has no formal charges, although it doesn't obey the octet rule and all that stuff. And then here, the formal charges don't make sense because this has a negative formal charge, whereas this is a positive. But we know chlorine has a more higher electronegativity than aluminum, so that just doesn't make sense. So therefore, that's why these exceptions occur. Resonance structures, basically, in some cases, 2 or more Lewis structures are not good enough. And they're not meant to be rotations of each other. The resonance structures are actually averaged structures. So, average structures. So, it's just basically, resonance structures are just using Lewis structures to denote multiple correct Lewis structures to denote the structure of a certain molecule or anion. And what you should note is that the actual structure is an average of each resonance, each Lewis structure. It's not, okay, there's a single bond and then all of a sudden a double bond here, then all of a sudden it changes there, then all of a sudden it changes there. No, it tends to be, it's across the entire molecule. And when we go to discuss bond order, that's going to be really important, because it'll introduce us to the idea there's actually, you can have fractional bonds more or less. So for example, here are 3 equivalent Lewis structures for carbonate. And the Lewis structure, it's important to note that all 3 carbon-oxygen bonds are the same length and strength. They are the same bond, quite literally. And the reason for that is that these electrons, which are known as delocalized electrons, they just tend to be scattered across the molecule, and they have an even probability of being anywhere in the molecule. So we draw these resonance structures sort of at the extremes, but even though we know it's an average, and we use Lewis structures because that's what we've been taught, but it's much harder to denote that, okay, there's like 3 electrons flying around the entire fucking molecule. So that's why we do that. Always remember that you can use these arrows to denote resonance structures, so denote between, so for example, when you draw resonance structures, you draw it out like this, with these double arrowheads pointing toward the possible extremes, I suppose, of each Lewis structure, and then you average it out to get the real structure. So it's something more like this. And again, because there's resonance, the electrons are moving across the entire molecule. They're not localized to one spot. And then bond order, it's a simple calculation. It's the total number of covalent bonds between 2 specific atoms in a resonance structures, between all resonance structures, divided by the number of resonance structures. So in the case of carbonate, it is a bond order of 4/3. We have, so let's focus on this. Okay. Let's focus on this oxygen carbon here. So we have 1, 2, 3, 4. 4 over 3 is 4/3. And lastly, we cover coordinate bonds, which are covalent bonds that consist of, basically, a coordinate bond is when 2 electrons come from one atom, when an atom shares both of its valence electrons. And you know what? This video is getting quite long, so I think I'll stop it here and go on to Vesper theory next video. Thank you very much for watching. Don't forget to like and subscribe.